the fMRI Analysis course for Python, hosted by Sinet again. So I guess like the first thing we're going to do today, so we're going to continue doing the notebooks today and cover a few more topics. And these topics will be things like how do you manipulate images using Python? How do you manipulate time series images in Python? So moving from 3D images like the T1 images to like the 4D images like functional images. And then we'll talk a little bit about parcellations and why we use parcellations. How do you apply a parcellation using the Python tools that we'll be exploring? And finally, we'll be covering the actual motion signal correction. So again, remember, all the images have been spatially aligned by fMriprep for us, but the actual signal artifact from people moving in the scanner, that we need to do ourselves. So we're going to actually be going over that. All right, so before I hand off the sort of the stage to Michael, who will be going over the first section, I'm just going to review, as I promised, the actual questions that were posted on HackMD, and I noticed that there's 2 questions that went up, and I'm super happy that you guys did that because that means you're enthused, and I'm also enthused that you're enthused. Okay, so let me share my screen really quickly so you guys can see that one. Share. Okay, so we got 2 questions from you guys yesterday, and I've sort of posted the answers in the actual Q&A, just so it's there for posterity's sake. So, come back in the future, you'll see that it's still there. So the first question was about the day 1 exercise. So whoever did that, thank you for actually doing the exercises. That's awesome. And the question is using layout.get space equals T1W okay for the functional data. So just to review what that is, so I'm going to just move there really quickly. Explore them for my prep. And these are the solutions, by the way. They're there for you guys if you need it, but I'm just going to do this really quickly. Over here. So in the second component over here, you want to get the native functional data. And what I did in sort of the solutions manual is I did the same thing that I did for the T1s to keep things consistent. But whoever posted that question, made an excellent observation that it looks like you have space T1W. So remember, when you're dealing with BIDS files, when you have a field and a value, so the field is space, the value is T1W, you can actually just go ahead and specify space as you did over here. So there is a space T1W in this case for the functional files. For the T1 files, for this version of fMRIprep, that doesn't exist. So if I were to replace this with T1W, and I didn't run everything before this, so I can't run it now, this will work. And this is just another way that you can get just the T1 space files. So that is actually a valid solution. Honestly, that's probably the preferred solution. And that's probably, for newer fMRIprep versions, this is probably the method that you're going to want to use consistently anyway. All right, so the second question that we got was asking about how do you guys get in touch with the neuroimaging community? So you've pointed out that for the R community, there's a ton of resources that you can go to in order to chat with the experts. And so Michael, my co-host, has answered this question nicely. So he mentions that what you could do is look at NeuroStars, which again, if in the HackMD, the NeuroStars link is right over here. And I'll just briefly show you what that looks like. So clicking over here, whoops, that did not open up NeuroStars. Okay, so the link is not working, but it is neurostars.org. So in neurostars.org, and it is basically a forum which has a bunch of sections over here, but you can basically go through, it's like Stack Overflow, if any of you guys have used it, where it's basically a question and answer format most of the time. There's also community chat. So neuro questions over here, everybody's just asking questions here. And if you have a question, it probably exists already in NeuroStars, and you can just search for it over here. And there's going to be an expert in the field or somebody who's worked with it before or gone through the same problem as you who probably has an answer for you already. So the second thing, I'll fix that link, but the second thing Michael mentioned is if you're using a specific software package, especially if you're using a specialized software package. Oh, the attendance code is 3. Thank you, Maurice. So if you're working with software packages, there's a ton of them out there. People are always developing their own. We do at our lab as well. You can use GitHub. So for people who are not regular GitHub users, GitHub is well, you should use GitHub first of all. GitHub is a repository for code, for collaborative coding, or for just hosting your code so you can have it online and available as like a version control. So in each software package's GitHub repo, so I'm going to go right here and go to GitHub. And then I'm going to look for nilearn. So nilearn is the neuroimaging tools we're using. So nilearn has a GitHub repo. If I click on it, it'll bring us to the code page. And over here, you'll see issues. If you click on issues over here, there are people asking questions here, and there are a ton of them. So typically, the developers are very open to answering your questions about nilearn. There's different labels for things, for if you want to label what your issue is specifically. So if you have a user experience problem, or you have questions about, you're running into bugs about plotting. So typically, these are more for bugs. NorthStars more so for questions. This is a great resource, and you can also like see what other people are asking and what the solutions to those problems are as well. And finally, there was a comment here where we have somebody asking, how do you post questions here? Great question. So the way that you do that is if you're on the HackMD page and you see this is the view that you see. You can't really edit. You can comment things, but you can't edit things. Then move to the top left corner over here, and you have 3 options. You can go into edit mode right here. So this will open up a markdown editor. Or I prefer this. You can go into both mode, where you get to see both side by side. So scrolling down here, the questions are right here. And you can literally, you don't have to do any fancy formatting. You can just say, hey, I have a question, and then type in your question there, and then we will just format it for you, just so things are nicely spaced out. All right. Okay, so with that being said, I think we're good to move on to the first notebooks. So I will hand this off to Michael. And again, remember to use the Jupyter Hub. It is the easiest way to do things, or use whatever method you used last time to access your notebooks. It'll still work the same. And Michael, if you want to take over.
All right, let me just make this text a little bit bigger. So did anybody have any trouble getting set up yesterday? Because we'll be running through a couple notebooks. So if anybody had some issues, we can run through setup again. If not, you can find the setup instructions on our setup page. So I'm going to be using the Jupyter Hub setup for these next few notebooks. And so I just went to njupyter.scinet.utoronto.ca, and I'm going to click into the STC bids fMRI folder. And then I'm going to head into code. And then we're going to go into basic image manipulation. And then, as Jerry pointed out, there's also the solutions notebooks as well. So if you fall super behind, that notebook is there for you to help you catch up. But also, if we're going too fast, or if you have any issues understanding something, feel free to post in the chat, and then we'll address those questions as they come up. And then Maurice made a good point. So before we even run any code, we're going to have to switch the kernel to the Python environment that we created yesterday. So I'm going to go to kernel, change kernel, and then click on stc_bids_fMRI. And to make sure you're in the right kernel, that should show up in the top right corner. So for this notebook, we're gonna look into learning more about nilearn and manipulating images. So if you came to the Intro to MRI workshop last week, we did a bit of image manipulation using nibabel. And nilearn actually makes this even easier. So nibabel is more of a low-level package that allows us to, access the data and the metadata associated with each nifty. But nilearn wraps up these kind of low-level commands into, syntax that makes more sense. So the first thing that I'm going to load is the pybids package, and that'll allow us to query our data for the right files that we're interested in. And the next thing I'm going to load are two functions from nilearn. One is the image package, or the image function. And the next is the plotting packet function. And for each of these functions, I'm just loading them with an alias. So I'm loading in image as img and plotting as plot. This is just for convenience sake. That way I don't have to type in image every time I want to use a function from the image package. So Paul had a question. I went through all the notebook files yesterday and noticed that for the later ones where you move the first 4 TRs, the data is sliced after the 4th index. Oh, so yes, this was, I think we'll get to that eventually, but this was intentional. So for a lot of fMRI scans, the first couple time points, they're typically called dummy scans. So these are time frames that have been acquired with high contrast, and after that the signal really decays. So what those high contrast images are typically used for is for head motion correction, because they have really good contrast. It's easy to align all the other images to those first few volumes. Mm-hmm. But for the purposes of analysis, we remove them.
I think Paul's asking because I think we say we're removing 4, but with the indexing, it looks like we're actually removing 3.
Oh, okay.
3 or 4 is usually kind of up to us. There's
Mm-hmm.
something actually, I think, in MRI QC that gives us an idea of that. Actually, also potentially in fMRIprep. But yeah, there's no 3 or 4 kind of standard.
Yeah. But yeah, that's a good catch. I think we'll update that as we get to that notebook. Thanks, Paul. So now that we've loaded in our packages, we're just going to start with selecting the files that we want. So I'm going to define the data path that we're interested in as the fMRIprep dir variable. And next, I'm going to use pybids to load it in as an object. And again, I'm just going to not validate it. And the next thing that I'm going to do is just add a new cell and select the files that we want. So we wanted to use the T1 files. So I'm going to do layout.get. I'm going to select a specific subject. So let's say we're just interested in the first subject from the data that we downloaded, 10788. I want the anatomical data. The suffix is preproc. I want the nifties only. And lastly, I want to return a file. The next thing I want is I'm going to do the same thing, except I'm going to grab all of the brain masks. So we're gonna select the same subject, the anatomical folder. Instead of using preproc, we're gonna use the brain mask suffix. Same extension. And I also want to return a file. So I'm just going to run that bit of code. Also, to run code, you can either click on Run here, or on the keyboard, you can type in Shift plus Enter. So now what I want to do is display both of the files that I just grabbed. So t1_files. Oops. And brain_mask_files. So you'll see that, oops. So for the T1 files, I get both the T1 in its native space as well as in the MNI space. And for the brain mask files, I get the same thing, both in the native space and in the MNI space. So that means our query worked. We got all the files that we wanted. Next, we're going to go over a couple of different image operations. So instead of using the MNI space for these next few steps, we're just going to stick with the native space. So what I want to do in order to grab that, I'm just going to use Python indexing to grab the first file from that list. So I'm just going to use 0 to grab the first file. And I also want to do the same thing for the brain mask. And the next thing I'm going to do is load both of those files using nibabel. So if you remember from last week, in order to load in a file, or actually this time we're doing it with nilearn, but in order to load in a file, I'm going to use the image function. And we're going to do img.load_image for T1. And we'll do the same thing for the brain mask. Is everybody following so far? You can type in the chat. Okay, great. So next thing that we're going to do is we're going to use nilearn's plotting module to actually look at our T1 image. Okay, Jane. Cool. Yeah, that's great. The solutions are there for you. If you run into any issues or questions while running the solutions, feel free to post in the chat, and then I'll just go back to help clarify some things. But yeah, now we're going to actually plot our image. And with nilearn, this is even easier than what we did last week using matplotlib. So I'm just going to use the plot module from Lino, and I'm going to call the plot_anat function on our T1 image. And it's just one command instead of that for loop that we did last week. So this gives us our image, and it by default gives us a slice on the 2, 3, and -15 coordinates. And you can see the crosshairs for where it's slicing our image. And I'm going to do the same thing with the mask. So I'm going to do plot_anat and do the brain mask. And this is what it looks like. So with our brain mask, each image that makes up the mask is a single number, so 1. And then each voxel outside of the mask is the same number, so 0. So that way, any voxels that aren't part of our mask aren't included. And with nilearn, we can also do some basic arithmetic on our images using the math_image function. And the way this is done is, if you remember last week when we accessed the actual data array of our data using nibabel, what we're doing with the math_image function is applying a formula to every single voxel in, or every single number in that array. So the first kind of formula that we're going to try doing is flip each of the signal intensity for each voxel in our anatomical image. So what's black is going to become white, and what's white is going to become black. So to do that, we're going to call this invert image, and we're going to do image.math_image. And so for the formula, it uses a mathematical expression. So here's just an example, a plus 1. In this example, what we're doing is adding 1 to each of the numbers in our data. So if we wanted to flip the color scale, we're just going to do, we can do 1 times -1, or sorry, a times -1, or we can just do -a. And then we're going to define a as our T1 image. And now we're just going to plot it just to make sure that it worked. And here's what it looks like. So as you can see, everything outside of the brain used to be black, and now it's white. So Maurice asked unauthorized question, is there a way to use condition expressions? Yes, you can, yeah. So I guess we can do that. So g.math_image, and we're going to do this do this expression on the brain mask. So a is greater than 125, and then we're going to call a equal to em_image. Wait, actually not, we don't want this on the brain mask, we want this on the T1. And let's plot it to see if it worked. Oops, I think we have to put this in quotes. So yeah, there we go. So this is what doing that gives us. It selecting all the voxels above 125, and we get this kind of outline. Honestly, making masks is probably one of the, I guess, the most difficult things to do from scratch. But yeah, it can be done. So this is just showing you a similar set of code. So we previously did this using the T1, the nibabel image object, or the nilearn image object that we loaded in, T1_image. But you don't even have to do that. You can do it right from the T1 file itself. And nilearn will actually load in the image behind the scenes and do all that for you. So the next thing we're going to do, and this is probably one of the most useful features, is actually applying our masks to our data. And to do this, it's pretty simple. So if we know that in our mask, all of the kind of voxels outside of the brain are 0, and all of the voxels within the brain are 1, what we can do is just multiply the T1 image by the mask image. So then everything outside, when it gets multiplied, it'll be 0, and everything inside the brain will stay at the same value that they were. So I'm gonna do that here. So our masked T1 is img.math_image A times B. And then A is going to be our T1, and B is going to be our brain mask. And then I'm just going to plot it to show what that looks like. So yeah, here's our masked image. So next we have an exercise that we want you all to try. What we want to do is try applying a mask so that the brain is removed, but the head is intact. So we're basically trying to do the reverse of this step. We want the outside of the brain, but maintain the inside. So does anybody have any suggestions for how we should do this? We've put in some example code, but the formula itself is missing. So how would you invert the mask? What should we make our formula? Here's a hint. We've inverted an image before. We've inverted our T1. Yep, that's great. Minus X. And if we want to apply our mask, what should the formula be? All right, A times B. Thanks, Katie. Oh, this didn't quite work.
It's actually shouldn't be negative x to swap values. Yeah, it should be 1 minus x.
Oh, right, because this is a mask, so that's why it's a little bit different. There we go. That looks more like it. So yeah, the difference is with the T1 we were inverting earlier, we were just flipping the sign. So here, if we wanted to make the 1 0 and the 0 is 1, we would just need to do 1 minus x instead of making it keeping the zeros as 0 and making the values inside the mask -1. So the next thing that we're going to do is slicing. So we did a bit of this last week using nibabel, but the syntax for nilearn is a little bit different. With nilearn, we have this function called slicer. So first thing I'm going to do is try and take out the 10th slice. So I'm going to call this x slice. And from our T1 image, I'm going to call the slicer function. And with nilearn, if you want to take the 10th slice, you have to specify a range. So we're going from 10 to 11. And then I want everything else in the y and z axes. If you remember with nibabel, what we were doing is taking our data and then taking the 10th index and selecting everything from the Y and Z axes. So yeah, with nilearn, the difference is you just have to be specifying a range. And how did you get the second line to put your code? Oh, to add a new line, what I did was, I think, so you can do, you click on this plus icon to add new code cells. The other way to do it using the keyboard is, I think it's, oh, you just have to type in A. Yeah, so just type in A in the keyboard. So slicing is also really handy for visualization purposes. So say we wanted to visualize a specific slice for our image. If you remember before, we plotted our anatomical image. Oops. So we'll plot our T1 image. And what this did is it gave us a default slice, so going at 2, 3, and -15. But if you wanted specific coordinates, we can use the cut chords argument and just specify them here. So I'm just going to say, let's say we want 50 on the x-axis, 30 on the y-axis, and 70 on the z-axis. And this should change the view. So ideally, you'd want something within your image just so that the z-axis isn't completely ignored. But that's all there is to it. So for this notebook, we just to recap, we covered doing some basic math on your images, doing some visualizations to see how those manipulations change your image, and also how to slice your image. So the next section, we're going to go even more in depth. So Katie asked, how do you change the crosshair position? So yeah, that was done using the cut coordinates argument. So if I wanted to, I can change that. And here I changed the coordinate, the z-axis to 30, and it changed where our z-axis was sliced. So if you don't use this argument, it gives you a default. I think by default, it tries to get the center of the image, but you can always modify it if you're interested in a specific view or if you're interested in a specific region of the brain. And oh, James said, I'm not following the keyboard shortcut. So yeah, there's multiple ways to run things in the Jupyter Notebook. You can use, I think this toolbar here will give you probably most of the functionality that you need. So adding cells, deleting cells, copying cells. But also if you click on the keyboard icon, this will show you all the possibilities. So here, when you click on each cell, it's highlighted in blue, and this means that I'm in command mode. If I double click it and it turns green, this means I'm in edit mode. So in order to use all these keyboard shortcuts, you want to make sure that you're in command mode, which is the blue. And then now, since I'm in command mode here, I'm just going to type in A, and it inserts a new cell above. And I'm just typing DD to delete them. So I'll hand it off to Jerry. So in the next notebook, we're gonna go even more in depth into nilearn and use some more interesting functions.
All right. Okay. So now we're going to move on to the next notebook. And this one is going to be how do we now, you guys have worked only with the anatomical T1 images so far. But now we're going to move on to actual fMRI data, so time series data. And this has a few caveats that you got to deal with when you're working with it in Python, but we'll cover it in this notebook and hopefully get you guys familiar with working with time series with 4D data. So first of all, we're going to open up this notebook. And so this notebook is going to cover the concepts of dealing with fMRI data. So remember that the data that we've been dealing with so far are 3D brain volumes. So we have an X, Y, we have a Z coordinate because the brain is a 3D object. However, when you're dealing with fMRI data, you are taking multiple like full scans, full 3D scans of the brain over multiple time points. So now you have many 3D sort of snapshots of the brain. And conceptually, you can think about it like this. So each of these, let's just pretend, is a 3D brain volume. It's a 3D array, if you will. And we have multiple samples of this 3D volume up to however many samples we have. So we're going to call that T. We have T samples. And the time between the samples, just some like background, is called the repetition time. So that's the amount of time that's required between samples. So the amount of time it takes to acquire a sample. And we have multiple of these. So we have a 3D image over multiple time points, which means we have 4D data. It is our fourth dimension. So dealing with 3D data is actually, I'm going to open up the chat because I realize it's closed. OK, so dealing with 3D data is actually really similar to working with 4D data is similar to working with 3D data, with the exception that now you have this sort of fourth index, which is the actual time point. So you have 0, 1, 2, 3, 4, all the way to however many samples of the full 3D brain you have. So we're going to work with it. We're going to work through this and start integrating functional data into what we're currently doing. All right, so we have some like boilerplate code that is here, so you don't have to go through. Yes, I can. I can make the text bigger. All right, how's that look? OK, so what we're going to do first is we are going to a little bigger. OK, let me see if I can do this in like a way that doesn't cut off. I might not be able to, but I'll just like make the text. All right, text, you're going to be even bigger. All right, how's that look? OK, so we're going to deviate from the solutions a little bit and modify these lines. So we want to work with M&I data only in this notebook. So to do that, all we have to do, again, remember when we're getting bids data, is specify space. So to each of these lines, I'm going to add space equals M&I 152 non-lin 2009C ASIN. All right. And we're also going to add return type. And as Michael did earlier, we're going to use return type file. So all I'm going to do now is I'm just going to copy and paste these to all my lines. Boop, like so. And now I have basically a whole bunch of files that are all MNI 152 nonlinear ASIM only. So we're just going to deal with those ones because that's typically what you'd use for a group analysis anyway. All right, so I'm going to run that line. And oops, I didn't specify my bids layout. OK, so I didn't. Wait, no, did I not import bids? I didn't import bids. How silly of me. Hold on. So first, we have to do the import. Sorry about that. So what we're going to do is we're going to do import OS. We're going to import matplotlib.pyplot as plot. So this is actually for an animation that we're going to show you in a bit. And then we're going to import nilearn. So from nilearn, import image as img. Again, what we did in the last notebook. And then we're going to do from nilearn, import plotting as plot. So these are, again, hopefully familiar to you guys. And then we're going to do from bids.layout, import bids layout. And then we're going to import numpy as MP to deal with arrays, since all data is represented as arrays. And finally, we're going to add a line, matplotlib inline. And so this enables you to make matplotlibs within the actual notebook itself. OK? I'm just going to reorganize my laptop computer so I can see the chat at the same time, so I'm not going too crazy. OK. Where are you? Give me 1 second. OK. OK, so if you're getting a module not found error, then you need to change your kernel. So again, remember, you have to go to kernel, change kernel, and pick SDC bids fMRI. And again, if it'll say kernel starting, and then once the kernel is ready, it should work. All right, so we're going to run this line. And it should run successfully if the setup is correct. Again, if this worked yesterday, it should work today. It's the same environment. OK, so once we've run that line, we can actually move on to running this line over here. And we've gotten our data now. OK, so let's just look at what our data looks like. And again, like I know I'm like super zoomed in, so you can't see as much of the screen anymore. So let me know if I'm going too far ahead and you guys are having trouble catching up. OK, so let's just take a look at the files that we have. So if I were to look at t1w_files, I'll see that what I have here is a path to the actual t1 MNI nonlinear file. OK, but this path is stored in a list. This is what these square brackets indicate over here. It's a Python thing. So in order to get the actual the file path out of the list, you have to use a normal Python index. So for example, you'd add square bracket 0. And now those square brackets that were in the print statement are gone. And this is just like a file path that you could use normally now. So we're going to do this for our functional files first. So our functional MNI file is going to be func_files 0. And then our functional MNI image, and now we're going to load in the file, is image.loadImage, and then we're going to do func MNI. And that's it. All right, so now we have our functional image loaded in as a nilearn object. We can start inspecting what it looks like. So first, let's get an idea of what we're dealing with in this moment. So first of all, let's look at the shape. So again, we can look at the shape by going to func MNI image and then looking at the shape property. And what you see here are 4 numbers. So the first 3 numbers over here, 65, 77, and 49, describe the 3D dimensions of each of those time points. So remember, functional MRI data is like 3D images of the brain, but across multiple time points. So each of these little snapshots, these 3D snapshots of the brain, are of this size. OK? And this last number over here just means that we have 152 time points. All right, so we have a 3D image of this size, and the last dimension again is the length of time, or the number of samples that we have, and that is 152. All right, so now let's start to getting an error after entering func MNI func files 0 and image.load func MNI. OK, so what does your screen, so what does func files look like to you? Is it a list of files? Is it empty? OK, I will Yeah, so it's empty. Okay, so that may mean that you might have typed this thing right over here. It's easy to get wrong. You might have mistyped that one right there. So make sure that the capitalization matches, that the entire little string over here matches exactly the same. Yes, I can enter that into chat, actually. So MRI non-lin 150, oops, 9C. Non-lin 2009C ASIM. Yes. So that's what it should be. Yeah, so you should paste it onto all of these lines over here. So it says space MNI 152 non-lin 2009C ASIM. And you paste it onto all of these ones over here at the end. Okay, so I'm going to move forward. Again, like we have helpers who can help you out. And maybe this would be an opportunity to get the screen sharing for the guests so we can actually like live debug. I'm not sure if that's possible. Sign it, guys. You can let me know. All right, so we're going to move forward. Again, the solutions have sort of like a slightly different version of it since we've deviated a little bit, but it'll still work the same. Okay. So going back here, the next thing we're going to do is deal with slicing with our 4-dimensional data. So again, remember in the 3D example, we used slicer, and we specified 3 numbers to say where x, y, z is going to be. So when we're dealing with 4-dimensional data, such as the functional MRI images, then you deal with 4 values. So again, we slice on the x, the y, the z, and now we can also slice across time. All right. So in this case, we want to pull the 5th TR, so the 5th time point. How would we do that? Does anybody know what to fill into these question marks? Yes. OK, so people are posting. We get a colon, a colon, a colon, which means we want to pull. Basically, what this means is that we want to pull all the x coordinates, all the y, and all the z. So you want to pull out a full brain picture. That's what this means. So spatial dimensions are the first 3 dimensions. And then finally, we want to pull the 5th TR. And if you remember, Python starts from 0. So to pull the 5th one, it's 4. And remember, since we're using slicer, we have to add a colon 5. It means 4 to 5, and Python, like the second number is exclude. So it's 4 up until, but not including 5. And then we can replace this question mark with this sort of like image that we've sliced. So func vol 5, plotting it. And this is our functional image. It is ugly, but that is the reality of MRI data. So this is showing the signal intensity for this particular time point for these slices of the image. So this is what functional MRI data looks like, except now you, instead of like this like sort of 2D, 3 different 2D views, you have a full 3D brain. And instead of this one volume that you're looking at, we have hundreds of these instead, and we have to analyze this data. All right, so the question, and a question that might be asked is, what does using 4 seems to give me the same image? Hey, if 4 works, this might be like we've updated nilearn across this workshop and many times that we've taught it. So if 4 works, then that is, it looks like it does work. So maybe you don't need the 4 to 5. So if that works, great, that's perfect. OK, so the next question is, what does fMRI data actually represent? And I keep talking about it like a time series data. And anytime people think of a time series data, you think about like a signal across time. So how does that look like in terms of fMRI data? So what we can think about fMRI data as is that for every voxel, so for every coordinate in the brain, we have a separate time series signal. So we can actually visualize what this looks like by saying, let's just say, so the question is basically, oh, sorry. The question is just basically this thing right over here. So we want to plot the sliced image that we got. So that goes straight into here. OK. So basically, what we can do is we can pull out a single voxel and then look at what that single voxel signal looks like across time. And that might give you like a better idea of what fMRI data is actually representing. So what we're going to do here is we're just going to slice our data. OK, so let's pick a single voxel. So our single voxel is going to be our func MNI image. And we're going to use slicer. And we're going to pull the, and again, I'm going to use a single number here because apparently it works. So we're going to do 59, 45, and 30. Again, deviating a little bit from the comment, but that's OK. And we're going to pull all the time points for this data. And then finally, we're going to use get data. And what get data does is it actually pulls the, yes, that's what, as Michael said, we're just going to plot the 5th time point. Thanks, Michael. OK, so we're going to use get data. And what get data does is it returns the data as a standard Python NumPy array, which is just how we deal with matrices and like multiple values in Python that are numeric. So I'm going to do that. And then let's take a look at the shape. So I'm going to do singlebox.shape. And what's happening here? Scalar indices disled. OK, so it's complaining. It doesn't want single values in your spatial dimension. So this is probably why I did that earlier. So we have to do our colons and 30 to 31. And if I run that, then that works. And so by adding these colons, we're just pulling out those particular slices. And that single voxel that we just pulled out has a dimension of 1 by 1 by 1, which is like a 1 by 1 by 1 section of our 3D image, which is a single voxel, like a single spatial index. And we have 152 in the 4th dimension. So 152 different data points for this 1 by 1 by 1 block of the MRI image. So what we're going to do now is we need to break this. So this is a 4D object. It has the 1 by 1 by 1, 1 by 1 by 1 by 152, which is 4-dimensional. But for plotting purposes, it's typically easier to deal with 1-dimensional arrays for a time series. So we're going to flatten this into a 1-dimensional object. And the way to do that is by saying that single box is equal to single box.flatten. So we're going to replace it with a flattened version because the first 3 dimensions don't mean anything. We already know it's one voxel. We don't need to know. It doesn't provide us with extra information. So, and then we can check the shape now. And by running that, now we have 152 values. And that's it. It's a single list of numbers. And these 152 values represent the signal for the signal across time for this one single voxel that we pulled out. All right. OK, again, post questions. If you have questions, be more than happy to help. I'm kind of rushing through because I want to be able to cover everything and not like have you guys not be able to see up to the compound section. So the next thing we're going to do is plot this actual data. So over here, I'm going to import matplotlib.pyplot as plot. So we've done this earlier in the notebook. We're just doing it again. And this is for Python standard plotting. So this is how you can plot like normal graphs in Python. And it's pretty similar to MATLAB's plot library if you've used MATLAB before. And what we're going to do is we're going to do plot.plot. And we're going to plot in the x-axis 0 to the number of time points. And to do that, we use a function from NumPy, which is like Python's array processing library, .arange. And we're going to start from 0. And we're going to go up to the length of the number of time points in that voxel. All right. So, and the next thing we're going to do, So close that bracket off. And then what we're going to do is we're going to point in single box. So these are the 152 different values that we've pulled from that single voxel. And we're going to color it black. So K means black. All right. So again, just to reiterate, plot.plot takes an x-axis value. So in our x-axis, we're going to have 0 to, in this case, 152. 151 because it doesn't exclude the 152 because 0 index. And in the y-axis, we're going to have the actual values, the signal values of the voxel, and we're going to have 152 of those. For each of those time points, we'll have one value. So once we're done that, I'm going to do plot.x label. Always label your x-axis. So this is going to be called time point. And then we're going to do our y-axis. So we're going to do signal value. And I'm going to run this piece of code, and this is what you get. So what this represents is across time, we have many different values. So this is the actual intensity of the signal for this one voxel across time. And that's what fMRI data is, except instead of one voxel, you now have a cube, like a cube of voxels. You have like maybe like 70 by 70 by 70, which is a lot of voxels of basically these signals. And we have to analyze this data, which gets super tricky. But there are tools for this, and that's what the neuroimaging community has been working on. OK, so this is just representing the idea that a voxel or fMRI data is literally just a bunch of voxels, and each of these voxels, which are like little segments of the brain, how do you plot all the time points? OK, so you can theoretically plot all the time points. I would not recommend it. But what you would do is you would extend this array. So you would have, you would basically have to, for each of your voxels, you would have to make a plot of the time series for that voxel. So instead of a single voxel, you'd have to take your entire cube of brain, your entire cube of voxels, and reshape it. So it is like a long array. Oh, plot all the time points. Sorry, I just read your question again. So this is all the time points for this one voxel. And if you want to plot all the voxels, typically, oh, no worries. Yeah. So if you want to plot all the voxels, that's kind of what we did, sort of did earlier over here. But again, you can't visualize 4D data. It is really hard to do that. So we typically like break it down into like either viewing a certain time point, or you're going to view a single voxel over time. There is usually never a case where you're going to be making this plot and then viewing like every single voxel's time series, because that just turns into a mess. There could be like, you're plotting 70 times 70 times 70, maybe different time series, and you're just going to get like a scrambled mess of lines. So typically you don't actually visualize the raw time series. Oh, no worries. All right, cool. OK, so the next step that we're going to talk about.
Can you just go back to the code? I think she was just asking to see the code.
Oh, I'm sorry. So here, does that help? OK.
Maybe post in the chat.
Yes. Let me just copy paste this into, where's my chat? That's the number one thing. And then there you go. OK. So moving on, again, just for time's sake, the next thing we're going to talk about is resampling. So remember in sort of like maybe in the last week's lectures, but I'm going to say it now, is that typically when you're acquiring MRI data, anatomical images are a much higher resolution in terms of the number of like pixels or voxels in a sense to represent the 3D volume. So you have a much finer grained resolution, much like when you have a computer screen, you have like a 1080p screen versus like a 720p screen. You can represent the same objects like a Chrome browser window, but with a different number of pixels. The more resolution you have, the finer the details you get. So the same deal applies to MRI images. And it turns out that anatomical images, since you only have one time point to acquire, you get a much finer grained resolution. So a 1 by 1 by 1, sort of like voxel size, so 1 millimeter by 1 millimeter by 1 millimeter, to represent one voxel in the T1 image. So you can have many more voxels representing the entire object, a higher resolution image of the brain. Whereas with functional images, you don't have the luxury of this high resolution image due to the physics of the scanner and overheating, and like you don't want to burn the participant's brain. That's the last thing that you want. So typically you have a much lower resolution image. So in this case, each voxel is 4 millimeters by 4 millimeters by 4 millimeters. So like a T1 image is like a 1080p sort of display, whereas a fMRI image is like a 720p display. They are different resolutions. And this causes problems because if you wanted to overlay our T1 image over our functional image, they are different resolutions. And so you can't actually plot them over each other right away. And you have to do something called resampling. And the easiest way that you can think of resampling is thinking about if you're working with PowerPoint or Photoshop, and you have two different images of different sizes. And the way that we typically do it in PowerPoint and Photoshop is that you stretch the image or you scale up the image in order to have one image fit the other. So you might make an image grow, which is like called, which is like downsampling in this case, or you can condense the image, sorry, upsampling, or you can condense the image, the larger image, down into the size of the smaller image, and that is downsampling. So we can either shrink the image or grow the image. And the same concept applies to neuroimaging data. So in this case, the fMRI image is the tiny image. The T1 image is high resolution image, is the large image. So what we can do is we can either downsample the T1 image, so shrink the size of the T1 image to match the fMRI image, or we can expand the size of the fMRI image, remember the lower resolution scan, to match that of the T1 image. And when you do that, you have to interpolate sort of the in-between values in order to get like a smooth, full image. Otherwise, you'll have holes in your image if you don't account for when you grow something, this extra space being created. When you shrink something, you have to condense the values together in order to match the size. Okay, so this is what you need to do in order to have two images match sizes together. And it turns out in the magical world of nilearn that this is relatively easy to do. So let's get our T1 image first. So our T1 MNI image is going to be from our T1 files, so T1 weighted files. And again, I'm just going to, and since we've already pulled out the MNI nonlinear files, we can just give it the 0. And again, just so it's clear to you guys, our T1 weighted files, again, is a list which contains a path to the MNI 152 nonlinear file right over here. So I'm just going to pull in that MNI file, and we're just going to load that in using nilearn. So image.load image and T1 MNI image. So run that piece of code. Whoops, T1 MNI image. OK. And now let's just take a look at what the size of this is. So I'm going to print out the size of the T1 MNI image. And again, to do that, you can use .shape. And just for comparison, let's plot what the the functional MNI image size is. And this is what we get. So the first line is the size of the T1 image. So this is a pretty large image. It's 193 by 229 by 193. And then let's look at the functional image, which is 65 by 77 by 49. And again, the last number is the number of time points, which tells us nothing about the size. It is a much smaller image. There's less voxels in this image because each of the voxels are bigger. So you need less of them to capture the whole brain. So now what we want to do is we want to resize one of these images to match the other. And since in most cases, you're analyzing the fMRI data, in this case, we're doing fMRI analysis. So we don't want to mess with our fMRI data. We don't want to scale up the fMRI data because then you're sort of like introducing interpolation, which is like guessing values in the fMRI image, and you don't want to do that. You want to mess with the data as little as possible. Whereas the T1 image, that isn't our main sort of analysis objective. So we can mess around with the T1 image. So what we're going to do is we're going to shrink down the T1 image to match that of the MNI image. And when you shrink or grow an image, you have to interpolate. Again, interpolation means guessing values. You either have to like condense multiple numbers together to make it smaller, to make the image smaller, or you have to guess values in between when you expand an image. And there's different ways to do this. So nilearn provides 3 methods of resampling. So there's continuous. So continuous is sort of like a way that you can you can grow or shrink an image, but do it so the image looks smooth. And so this is really good for structural images because it preserves edges. The second method is linear. So linear is sort of like the standard way of what a lot of image processing tools use. And it basically takes averages. It kind of blurs the image together in order to guess values in between by saying like, I have value 1 and value 2. Let me like take the average of those 2 to guess what the value in the middle should be. That's linear. And finally is nearest. And what nearest does is it says, OK, so if I'm going to expand an image, let me take that like new voxel that I have to insert now to fill the gap and look at all the neighbors. What is the most abundant number in my neighbors? So what is the most what is the mode basically of all the neighboring voxels, and pick that number. So what nearest does is it doesn't guess in between values. It picks the most frequent value that surrounds the new voxel that's being injected. And again, this is really useful because you don't get in between values. So if you have a whole bunch of like 3s and 2s in your image, intensities are 3s and 2s, then you won't get like a 2.5. And this is really good for masks because in masks, we just want 1s and 0s. We don't want 0.5 and 0.2. And so by using nearest, we make sure that we keep only 1s and 0s. We don't guess averages of 1s and 0s, which might give us like a 0.2 or something. And so they have different use cases. And over here, we're going to just do one resampling interpolation, and nilearn does all of this hard work for you. So I'm going to make an object called resamp_t1, and we're going to do image, resample to image. So the affine matrix is actually, the affine matrix is independent of the, the affine matrix does change. The only thing that changes from the affine matrix is the diagonal of the first 3 columns. And that diagonal represents how much you have to scale a voxel by, right? So when you shrink down an image, those 3 numbers in the diagonal will change, which means like your voxels are different sizes. So again, the affine matrix represents how do you transform from a 3D array into coordinate space, as in millimeters. When you shrink down all your voxels, then the size of each voxel is changing, and therefore your affine matrix has to be adjusted to say, now the voxels are smaller. I must scale differently in order to translate into millimeters. OK? So, and nilearn handles all of this for you. It's magical. OK, so the first thing I'm going to do is give it a source image. Again, if you hit Shift-Tab, it'll tell you all the arguments that you need. And we're going to feed it the T1 MNI image. And next, we want to specify the target image. So target image. And this was the func MNI image. And finally, we want to say what kind of interpolation we want to use. So I'm just going to scroll really quickly. And in this case, since we're using a T1 image, we want to preserve images. We want to preserve edges. We don't want to blur them out. We're going to use continuous. OK? So this is going to shrink down the T1 image to the size of the functional image, but do it in a way that preserves sort of the edges. So we don't want to blur out the edges. We want to keep like a well-defined T1 image. So I'm going to move this to the next line so it's a little bit easier to see. And now what we can do is we can print out the shapes. So resampt_t1.shape. We can print the func MNI image.shape. And we can just do plot.plot_anat. And let's plot our resampled T1 image. OK. So I'm going to keep this here for a bit, but when you guys hit enter, now look at your first 3 dimensions, they match. So the T1 image, which is the first thing that we've plotted the shape of, now is a lot smaller. It matches the fMRI image, perfect. And finally, the fMRI image obviously doesn't change because we didn't change it. And if I scroll down, what you can see is, it might be a little bit hard to tell, but we have a blurrier version, like a more pixelated looking version of our anatomical image. It's not as sharp, and this is because we downsampled it. We shrunk the size of the image. We reduced the resolution so we get more blocky picture. Okay, and so this is just a quick animation showing what this looks like. So you can just run these two pieces of code and these three pieces of code, and what you'll get is you'll get this image right over here. And if I press the play button, you can see sort of the transition between the resampled image and the original T1 image. One is sharper, one is blockier, and that's what resampling does, okay? All right, so we're not going to cover the exercises. I actually recommend that you guys try to do this on your own. And if you run into problems, again, let me know or post in the HackMD, and then we'll go over it. But for the sake of time, we're going to move on to the parcellation section just so that we can get as much covered today as possible. So I'm going to hand it off to Michael. And we might cover the confound section tomorrow instead. That won't take too long to go to, and then we can do the assignment afterwards.
Okay, so now we're going to go to the parcellations code, and that's going to be notebook 5, applying a parcellation. And so here we're going to be talking about brain atlases. So in our MRI image, what we can do is similar to, an atlas of different countries. We can create atlases of the brain where each voxel has a distinct label. So I think there's some examples linked over here. But yeah, people have been creating atlases for a long time. Some of these are to define specific anatomical regions of the brain. Some of these are to define functional connectivity networks. So depending on the type of analysis you're doing, you can select an atlas that would be relevant. nilearn itself has a bunch of atlases that you can fetch using their nilearn datasets function. And these are all listed here. You can also download any atlas from the internet and use that in your own atlas if it's not listed within the nilearn dataset function. We have a paper listed here, Arslan et al. 2018, which kind of goes into more detail about atlases, and also Aaron has done a lot of comparison between different atlases. But some of the handy features are if you have your fMRI image and you're noticing signals of activation in specific regions, what an atlas can do is tell you what exact region those signals are occurring in. It can limit the number of statistical tests. So say instead of running your statistics on each individual voxel, you're running them on a group of voxels defined within a region of interest in the atlas. So the first thing that we're going to do is retrieve the atlas. Let me just open my chat to see. So we're going to import all of the functions that we need for this. So from nilearn, I'm going to import datasets, image, and plotting. And first we want to get for this example, we're going to use the EO 2011 atlas. That one is stored in nilearn, and you can grab it using the fetch atlas EO 2011 function. So I'm going to define a folder where we're going to download the atlas to. I'm just going to call it resources/ROIs. And then next, I'm going to fetch the atlas. So using the datasets function from nilearn, fetch atlas _EO _2011, and type in my atlas directory. Oh, yep, I can make it bigger. Does that help? So I'm just going to go into, I'm just going to open a terminal just to show you what exactly we downloaded. So if I go into the bids fMRI folder, and then I go into the resources folder, ROIs, here's the YEO 2011 folder. And you'll see that we have a bunch of different atlases. So we have the 7 networks and the 17 networks. In the YEO atlas, they define different functional connectivity networks. So they have 2 different kind of versions of this. One has 7 different regions of interest, and the other one has 17. It also comes with a mask and a color lookup table. So this will define the colors that are associated with each individual ROI. So I'm going to go back to here. And we can look at the keys of the atlas using the keys function. Yeah, and Katie asked, do datasets create that directory, or would we have to set up the directory structure first? And yeah, the function actually created everything. So we defined this directory, and it didn't exist previously, and the function did all the work for us. Yeah, that's a good question. Sometimes functions don't do that, and we would have to define our directory ahead of time. And Paul was asking, would it be possible to get the details of the assignment? So actually, what we're going to cover is ask you to do the exercises on your own time. And for the assignment, we'll be walking through the assignment will be the final notebook 7. So we'll work on that collaboratively tomorrow, and then we can maybe take it up towards the end. So when I do Atlas keys, it's showing me all of the different functions available to us. So we can, or all the different files available to us. So the next thing I'm going to do is actually plot the different atlases. So I'm just going to put in some default values. So I want to put my crosshairs on this coordinate. I'm going to show the color bar, and I'm going to do a paired plot. So that means that the colors on both the left and right hemispheres of our atlases are going to be the same. And then I'm going to use the plot ROI feature. So instead of using plot EPI or plot map, we're going to do ROI, atlas YEO, and to grab each atlas, we're gonna access it using the index associated with the right key. So here I'm going to plot the thin 7 atlas, and I'm going to give it these coordinates that we defined earlier. Oops. Key air thin 7. Did I?
Use an underscore. It's not a dash.
Right.
Yeah.
Good catch. And then for the title, I'm just going to call it thin 7. So there we go. And we can do the same thing for the other atlases. I'm just going to plot maybe the thick 17, just to show you the difference between the two. So here's the thin 7, and here's the thick 17. So the difference is the 17 has 17 regions of interest, and the space that each region of interest takes is much larger. So the next thing that we're going to do is, oh yeah, so we chose the 7 network. We're going to use the 7 network atlas going forward. And these 7 networks are defined by the U atlas to include the background connectivity, visual connectivity, somatosensory, the dorsal attention network, ventral attention network, the limbic network, frontal parietal, and the default network. And what we're going to do next is I'm going to create a variable just to select the thick 7 atlas. And what we're going to do is we're going to split all of the ROIs into, or split our 7 ROIs into different segments. So what you can see here is there are some ROIs that are spatially far apart. And what we're going to do is assign them to different colors. So I can show you what that looks like. We're going to use the connected label regions function from nilearn. And then we're going to use this function to reassign some of the labels. And then I'm going to actually use a couple different coordinates just so that you can see what that looks like across different sections. Oops. And I just wanted to, I'm just going to display the z-axis. So looking axially. Forgot the bracket. And so this is taking a while, but it'll pop up shortly. So this is what it looks like. So now each of our 7 networks have actually been split into 49 different regions of interest, as you can see here. And areas that are far apart spatially are now coded with their own unique color code. The last thing that's really important is to resample the atlas. I'm going to leave this as an exercise in the interest of time. And so what Jerry highlighted in the last notebook was resampling the T1 image to the fMRI image. And we're going to have to do a similar thing with the atlas. We're going to have to resample the atlas to the fMRI image in order to actually plot them on top of each other. So we'll leave that as an exercise, and we'll we might do a recap tomorrow morning.
Great, thanks, Michael. So, so since we're out of time, issues pop up and things take longer than you think they do, but that's totally okay. So what we'll do is we'll cover the rest of this notebook tomorrow in that session, as well as the one more session, which is on confound regression. That one is actually pretty short and won't take up too much time. And then the rest of the time will be dedicated towards the assignment. And again, if you have any questions, post it in HackMD. And I'll stay around for I'll stay around for like 5 minutes just to help debug any residual issues. And then I guess we'll see you guys tomorrow. Thanks for attending.